Today, we're going to talk about something truly revolutionary, a machine that actually learns from its own experience. We are diving into the Perceptron, which was the very first practical neural network. Really, it's the granddaddy of all modern AI. Let's get into it.
So I want you to picture this. The year is 1958. Over at Cornell, a psychologist named Frank Rosenblatt builds this, the Mark I Perceptron. And yeah, it's a room-sized beast of a machine, a total maze of wires and motors. But it was designed to do something that had never really been done before. It was built to learn. Think about that for a second. It was designed to learn a rule simply by looking at examples. This wasn't some abstract theory on a blackboard. It was a physical, whirring, clicking machine that was demonstrating the core idea of artificial intelligence. It was, for all intents and purposes, the birth of the artificial neuron. All right, so here's our game plan for this explainer. First, we'll talk about what made this learning machine such a big deal. Then we're going to pop the hood and see exactly how the Perceptron learns. After that, we'll look at the incredible hype and a pretty critical flaw. And finally, we'll see why it's still the bedrock for all of the AI we use today. Okay, first up, a machine that learns. We're about to look at a whole new class of algorithms, one inspired not just by numbers and stats, but by the amazing structure of our own brains. You know, so far, we've explored this amazing toolbox of machine learning algorithms, right? We've got regression for predicting values, classification for sorting things into buckets, and clustering for finding those hidden groups in our data. Well, neural networks, the one we're highlighting here, are a whole other family of tools in this box. And the very first big one to make a splash was the Perceptron. Okay, let's get into the fun stuff. How does the Perceptron actually work? You know, the core idea is shockingly simple. It basically translates what a biological brain cell does into some very, very straightforward math. So just think about a real neuron in your brain for a sec. It's got all these little branches soaking up tiny electrical signals from its neighbors. And if the combined punch of all those signals crosses a certain line, bam, the neuron fires and sends its own signal down the line to other neurons. The Perceptron is just a mathematical copy of that exact idea. An artificial neuron takes in a bunch of inputs. That's our data. And for each input, it assigns a weight. You can think of a weight as just a measure of how important that input is. Then, the neuron just adds up all those weighted inputs. And if the total is high enough, it fires. It outputs a 1. If not, it stays quiet and outputs a 0. Simple as that. So you can really boil this whole thing down to 4 simple steps. It gets inputs, multiplies them by their weights, adds it all up to make a decision, and then produces an output. That's it. That's the recipe it uses to learn how to separate two kinds of data, like, say, a spam email from a real one. But that brings up the single most important question in all of machine learning, right? How in the world does it figure out the right weights? How does it learn what's important and what it should ignore? Believe it or not, it starts by just guessing. The whole algorithm kicks off with a completely random set of weights. Then it starts looking at our training data one piece at a time. It uses those random weights to make a prediction. In this case, it's trying to draw a line that separates the circles from the triangles. And as you can plainly see, its first guess is not great. Now, for every single example, it checks its work against the correct answer. If its prediction was right, it just moves on. No change is needed. But if it gets one wrong, like this point right here that it misclassified, it knows it has to fix something. And when it makes one of those mistakes, that's when the magic happens. The algorithm adjusts its weights just a tiny, tiny bit, basically nudging that decision line in a better direction. This super simple rule, if you're wrong, adjust, is the absolute heart of the learning process. You do that thousands and thousands of times, and that line gets closer and closer to being perfect. And this brings up a really important distinction we need to make. The Perceptron algorithm is the training process itself, that whole step-by-step method of guessing and nudging the weights. The Perceptron model is what you have at the end of all that, a fully trained neuron with its weights locked in, ready to go out and make predictions on new data it's never seen before. So as you can imagine, the world was going absolutely nuts for this new invention. But like with any brand new technology, it came with a ton of promise and some pretty serious limitations. I mean, Rosenblatt's demonstration completely captured the public's imagination. You had headlines talking about electronic brains. For the very first time, people could see a physical machine that you could literally teach to recognize shapes and images. It made this abstract idea of an intelligent machine feel incredibly real. But, behind all that excitement, researchers were finding a huge weakness.
The perceptron could only solve problems that were what we call linearly separable. That's a fancy way of saying you could draw one single straight line to perfectly split the two groups. It got totally stuck on a classic puzzle called the XOR problem, which you see here. No matter how you draw a single straight line, you can never separate those points correctly. This was a massive problem.
Now, that limitation, it was a huge deal. It actually caused a kind of downturn in AI research for a while. But even with that flaw, the perceptron's legacy is absolutely everything, because it laid the groundwork for all the incredible stuff that came later.
And here it is, the big takeaway. The modern deep learning networks, the AI that powers pretty much everything cool today, are really just massive, massive collections of these simple perceptron-like units. By stacking them up in complex layers and using smarter training methods, they blow right past that original limitation. Every single complex neural network today has the DNA of Rosenblatt's original perceptron deep down inside.
And that's the story of the simple little machine that kicked off a revolution. Thanks so much for watching. Knowledge Equity Partners is a multilingual channel where we share contemporary and practical knowledge on a variety of topics that can enhance your daily lives to make it more effective and efficient. So hey, if you find our content valuable, please subscribe to Knowledge Equity Partners so you'll get notified about our daily videos. And don't forget to like, share, and spread this valuable practical knowledge with your family, friends, and your community. Let's together keep the quest for knowledge always high.
So the big idea was to stack these neurons, right? Create layers. But there was a massive problem. For decades, nobody knew how to actually train them efficiently. Next time, we'll explore the incredible breakthrough that finally solved that puzzle and unlocked the true power of deep learning. We'll see you then.